Alright, this is Mr. Sindel. I'm recording a video in advance for you 8th graders. These notes can be found on the website or on Google Classroom, however you want to find them. So far in class we've covered a few things. Here are my quick notes. We know how to convert a fraction into a decimal. We know how to take the square root of a fraction. We know how to estimate square roots, like in between what two whole numbers. And we also know how to convert a decimal into a fraction. I haven't taught you any of that. That's just review at this point. This is something that might be new now. So let me go ahead and title this. Our new date is going to be, well, today's the 6th, so tomorrow's going to be the 7th, 9/7. And this is going to be talking about sets of real numbers. So the older that you get, the more that you learn about math, the more you learn about types of numbers. And you've already seen these before, but I'm just putting a name to them. So the first numbers that we ever discovered from like humans were the counting numbers, natural numbers. So I think your book calls them whole numbers, which is, it's not correct. So I'm going to do like this little diagram. And I'm going to have this box represents every number that you've ever seen. And that box will get bigger and bigger, especially when you go into high school. And there's going to be two sides of our box. And if you've seen the homework, you'll see the same shape come up. So on the very inside, the innermost level, you have whole numbers. But that is a terrible name, and I'm not going to call them whole numbers. Your book calls them whole numbers. I'm going to call them natural numbers. And an even better name for them that sometimes I'll use is counting numbers. So I think my box is going to have to be a little bit bigger, but I'm going to erase my box for now, I think. Counting numbers are numbers like, how many things do you have? Well, I can have 0 of something, I can have 1 of something, 2 of something. If you're counting the number of apples that you have, you can have 2 of them. If you're counting the number of people in the room, you can count 3, but it wouldn't make sense to say there are 3.5 people unless maybe the person is weirdly cut in half. Counting numbers are usually whole numbers, so I can understand where this word is coming from to help students understand it's not a partial. It's not like 1.5. So if you're counting the number of sheep and stuff, right? So that's the first layer. But there's a problem with that, which is you don't have negative numbers. So inside of that, maybe I'll make that a circle. So this is contained within a set that is called integers. Integers contain whole numbers, but they also include more. So yes, integers still contain 0, 1, 2, and 3. I mean, the circle in here is inside of integers, so all of the 0, 1, 2, and 3 is already contained in here, but it also includes even more. It includes negatives. So that's the big thing. It's negative whole numbers. So you can have a -3, a -2, a -1. All of those are now allowed. So it has unlocked the potential to do negatives. And I'm realizing that this is a little bit off to the right. So move to the left. And then finally, in this outermost layer, what we have is, actually I'm going to move this, I'm realizing I want some room up, so I'm going to move this down. We have rationals, which again, it's a good word because it has this word ratio in it. Ratio literally means a fraction. So another way of thinking about this, if you don't like the word rationals, I do like it, but you can think of this as the word fractions. Most of what everyone knows are fractions. It's very weird to know something that isn't a fraction. If you give me a number like 1/2, that's obviously a fraction. But Mr. Sindel, 0.53, that's not a fraction, that's a decimal. And then I can say, I can convert that into a fraction though. I can say that is 53 divided by 100. As long as you have a decimal where the numbers repeat, they have some pattern to them, it's going to be a fraction. It's going to be irrational. And we saw how to do that, right? We saw, oh, if I have 0.123 and it repeats 1, 2, 3, 1, 2, 3, 1, 2, 3, that can be turned into the fraction 123 divided by 999. As long as there is a pattern that repeats, I'll say that again, with the decimals, it is a fraction. It is a rational number. And if it obviously is a fraction, it is a fraction, like it belongs in this group. And technically, rational numbers include whole numbers as well, because watch, if I write 1 over 1, that is a fraction, and 1 over 1 is really just 1, which I've already listed over here. 1 is a natural number, 1 is also an integer, and 1 is also a rational number. So 1 belongs to all three of those groups. If it's in this center one, it's also in this one, and it's also in this one. That's what I'm using the word sets. I'm kind of containing them all in this one set. So the way that sets work is a half belongs out here, but a half, and maybe to be more specific, I'll erase this 1 over 1. A half cannot go in here. A half does not belong into an integer. An integer is a whole number, and a half is a half of a number. So I think this diagram hopefully makes sense. But you have the other side, the dark side, right? You have the non-fractions. Non-fractions. And there is a term for that mathematicians use, which are called irrational. But I don't like that word. It's okay, but it makes more sense to call them non-fraction numbers. Non-fraction numbers are in their own set. They are not self-contained. Notice it is a completely different little bubble here. So give me an example of a non-fraction. Most students will struggle with this, but some of the more famous numbers come to mind, like the number pi, which is 3.1415926535897932384626433832795028884. It goes on and on forever with no clear pattern, and it never has repetition. This is an irrational number because there is no pattern with the decimals. There's a bunch of other numbers. There's like Euler's constant, 2.71828, blah blah blah. There's phi, which is a number that you'll learn in high school, which is 2.6180 something something something. Again, these numbers go on and on forever. I would say these two you don't really learn about until high school, so maybe you can just cross them off the list for now. These are the three most famous constants that go on and on forever that are irrational, but there's also a bunch of other numbers that are irrational, like the square root of 2. The square root of 2 is irrational because if I write it out and I have let me pull open my calculator. If I type in the square root of 2 on my calculator, watch what happens. If I do the square root of 2, look at that decimal over there on the right. 1.414213562. Like, there's no clear pattern. It will never repeat. The square root of 2 is irrational because when I look at, well, there's a lot of reasons, but to us, it looks like when we put it in the calculator, there is no repetition with the decimals. So the square root of 2 is irrational. It's about 1.3-ish. That's all you have to remember. 1.3 ... Basically, any square root is irrational as long as it's not a perfect square. So you're like, okay, square root of 3, yep, that belongs here. Square root of 4, wait a second, isn't the square root of 4 just 2? And 2 is a whole number, and it's a natural number, really. It belongs over here with the whole numbers, the natural numbers. So I have to undo that. The square root of 4 does not belong here. Square root of 4 actually belongs right here. Square root of 4 goes into the counting numbers. It's a little bit weird to say the square root of 4 because it's really just 2, but it does belong over there. What about the square root of 5? Yep, square root of 6. You might think, oh no, well 6 is even. Nope, it still belongs over here. Unless it's a perfect square, it will stay in the non-fraction, the irrational realm over here on the right-hand side. It doesn't matter if it's to the right or left. It's its own separate bubble. Square root of 7, square root of 8. What about square root of 9? Does that belong here? And I'm hoping you're screaming at the screen, no, it does not belong here because square root of 9 is 3, and 3 is a whole number. It's a natural number, so it comes back over here. So I have to move square root of 9. Go back enough. Square root of 9 actually belongs right there in the natural numbers. So there's an infinite number of non-fractions, because you can clearly see that this list goes on and on forever, and you just have to skip every time you get to a perfect square, like 9, 4, 16, 36. All of those square roots belong in the natural numbers. So that's to help give you some idea of the difference between things. Let me give you an example. I'm just going to continue on with my notes. So I'll have you say, classify each number. Oh, my handwriting could be better. Number. So I'll give you like 3 of them. A, B, and C. So let's do the number -3, square root of 36, and pi, sure. So they will have many names associated with them. Usually they'll have many. Sometimes they'll only have one. For now, we'll come up with more names when we're in high school, once you learn about the shadow dimension and other cool things. So first of all, -3, does it belong to the most inner circle? The most inner circle is the natural numbers, and it doesn't make sense to count a negative number of sheep. I always think about counting sheep because the earliest known cases of humans knowing about numbers is you look at like ancient staves that people used to have, and they would have like counting marks on their staves, so that when you're like herding sheep, you would remember, oh yeah, I used to have 8 sheep, but now I have 7, so I think a coyote got one of them, or something like that, right? It's just you wanted to keep track of the animals that you are currently herding around. So it's not a counting number. You can't have -3 sheep, so it doesn't belong to that innermost layer. So it doesn't belong here. Well, does it belong in the integers? And because integers have unlocked negative numbers, it does have the name integer. But that's not it. It has many other, well, at least one other name. So I'll say this has the name integer, but it has other names, because if you are an integer, then by default, because you are inside this bubble right here, you're also inside of that bubble here. You're also a rational number. You can call it a fractional number if you want. Names are just names. If you want to be very technical and be like a correct mathematician, you'll use the word a rational number. So I'm going to use that correct word. So this is an, I don't know why I did integers. It's an integer. It is also a rational. And technically, I don't think, oh yeah, it does do this. Everything in these two fields, both of these are in an even more mega bubble. There's like this mega bubble that everything is part of. Everything here is just called a real, which is, if you ask me, is silly to start teaching you about in middle school, because you don't know what a number that is not real is. But there are fake numbers. Oh, that's a terrible word for them. There are imaginary numbers is the technical term for them that you will learn about in Algebra 2. There are real numbers and there are imaginary numbers, but it's really the shadow dimension. So these are non-shadow numbers that you're learning about right now, and eventually you'll learn about shadow numbers later. So technically it's also real, but again, it's really silly to call them reals because you don't even know what imaginary numbers look like. But it is technically a real. I'm being technically correct, and this is what the book and the test and everything is going to be expecting of you guys. All right, what about the square root of 36? So the first thing that I note is the square root of 36 can be simplified, right? The 36 is a perfect square, so if I rewrite this, this is really equal to 6 squared inside of a square root. And one of the cool things about a square and a square root is they're opposites. This and this cancel each other out, and then you just kind of scribble that out, and what's left? Just the 6. So the way that I usually show my work when I do that is I cross the 2, I cross the square root, and I say, okay, that's equal to just 6. So really, the number 6 is a natural number. It's a counting number. Like you can have 6 sheep. So the first name that this has is it is a natural number. What else is it? If it's a natural number, by default, the natural number is inside. This natural number is inside an integer, so it's also an integer, and it's also rational, and it's also real. You just kind of, like Inception, you go out through the dreams, you go out through the bubbles on your way out. So you have to say it's a natural, it's an integer, it's also a rational, and it's also real, not imaginary. What about pi? So pi doesn't belong over here anywhere on the left-hand side because it doesn't have a clear pattern. When you don't have a clear pattern, you're considered an irrational number. You cannot write it as a fraction. It's interesting that this is still being taught in elementary school because to prove that it's irrational, to really know in your bones, you're like, oh, well, maybe those digits will repeat. Maybe if I had 1,000 digits, they would repeat. Is there any way that I could prove that they don't repeat? And the proof, again, you get to see it in high school, how to prove that pi is irrational. So for now, you're just going to have to take my word for it. The proof is a little bit difficult, but I think if I spent a week with you guys, we could prove it. It is irrational. That's the first thing that pops out. Irrational. Again, this word just means it cannot be written as a fraction, and anything that is rational is real. For you guys right now, everything is real. You don't know about the shadow dimension, therefore everything that you know about is real. Cool, so that's how you're going to classify numbers. I think there are going to be some homework assignments that will help you with questions like that. Is there anything else I want to say? Oh yeah, so one of your homework assignments eventually is going to have a problem where you multiply fractions, and I just want to make sure that you know how to do that. So let's do the next topic, multiply fractions, as a review. Multiply fractions, which is much, much easier than adding fractions. And it's weird that I'm looking through here and there is no adding fractions. But there's a problem in the homework that looks similar to this. I'm just changing the numbers a little bit. 3 over 5 times, I don't know, like 15 over 9. And they're asking you the question, what type of number is that? Is that irrational? Is it real? Well, I mean, everything is real, so the answer is yes, it is real. But how do you do that? So just as a quick reminder, the way that you multiply fractions is straight through, and you just multiply. So this is really equal to, if I'm showing my work, it would be 3 times 15 in the top. The top is also called the numerator. And in the denominator, or the bottom, you have 5 times 9. And there's the slow way of doing this. The slow way of doing this is to actually multiply those out. So I'll show you the slow way, but I'll show you the fast way also in a sec. The slow way is saying, okay, 3 times 15 is 45. 5 times 9 is 45. And 45 divided by 45 is 1. So that's a slow way. The faster way would have been to go like this. You say, oh, well, 3 and 9 can cancel out. 3 would turn into a 1, and 9 would turn into a 3. And you could do the same thing with the 15. So you say the 15 and 5, I could divide those right now. I know 15 divided by 5 I can do in my head. That's going to be 3, and that's going to be turning into a 1. And then really quickly I could say, oh, that's 3 and that's 3. Everything is canceled out. If everything cancels out, you're left with just 1. Maybe you think that's the longer way, but that's the faster, more efficient way if you start using that method of cross-canceling. Anyway, getting back to the question, what type of number is 1? Well, very much like the number 6, it is a natural number because you can count sheep with it. It's an integer. Integers just unlock negatives. This isn't a negative. I didn't even need it, but it is technically an integer. It's also rational. It's also a real. So it's all 4 of those things. Nice. Looking through these questions. Is it possible to count the number of rational numbers there are between 2 integers? Whoa, that is a deep question. I think I'm going to have to wait for another video to talk about rational numbers. How many rational numbers are there? Are there an infinite? Are there a finite number? So wait for the next video. Thanks for watching.